will start with Giuseppe Sergioli, a quantum approach to pattern recognition.
Thank you. Thank you very much. Okay, so as a beginning, I really like to thanks all the organizers and most of all Thomas that is busy as well, and for this very nice occasion to meet together, to put together different competencies and height level, I think, of different competencies, at least till now, at least till this talk. So, what I'd like to introduce today is a kind of quantum approach from pattern recognition, and this is a work made with Roberto Giuntini, that unfortunately that cannot come here, and Martin Bosic, that is just at the end of this room, and this is the partial result. It's still a work in progress, but it's a partial result that is given by arising from a project that is called Modeling and Uncertainty Quantum Theory at the Service of the Pattern Recognition, that was made in Cagliari between the Department of Philosophy and the Department of Electronic Engineering. Well, the list of content of this talk is, at the beginning, yeah. Sorry? Two departments. The first is Department of Philosophy because I am affiliated to the Department of Philosophy. Yeah. And the other is the Department of Electronic Engineering. I'm a physicist that study logician that study logics in the Department of Philosophy. It's quite scrambled, but it's the history of the problem. Well, in this context that we are multidisciplinary, it fit quite good, I think. Well, the list of contents, as I said at the beginning, I'd like to introduce you some really basic element of pattern recognition, just in order to provide a kind of quantum representation of this, that we will call inspired quantum pattern recognition on a classical computer. That will be the main important part of the talk. I will stress just a little bit one looks like a problem. It is the not invariance under rescaling, and at the end I will show some practical implementation. But first of all, let us fix some names. Let us fix some detail that will be fundamental. Thank you. Will be.
I'm sorry. Can I also see the stream as storage quickly?
Yeah.
Okay.
Yep.
I'm sorry.
You're welcome.
Okay, let's start quickly. Okay, thank you. I'm sorry.
Okay, so first of all, let us consider as an example two disjoint set A and B of different objects, as today we have already seen, the set of cats and the set of dogs. The first process is called the training process. In this process we consider this set, we consider the big set of given the big set of all the cats and all the dogs, we can consider just a subset, we say CA and CB. It is called like a training set that is in most of cases just a random selection. And from this, we just select this subset, and for each element of this subset, we decide, for instance, XA, we decide to make measurement on two or more features. That can be, for instance, the weight and the length of the tail and so on. So we can associate to each element of this subset a vector whose components are given by these features. For instance, XA1, XA2, and so on, and so on. So in the most simplest case, we can consider just two features cases, but in the most general case, the number of features can be even quite big, 7, 10, 100. Well, the point is that this set is that set CA, CB are called the training set. The XA, this element that belongs to CA, is called pattern, and each pattern is univocally determined by its features. So we can consider just from an algebraic point of view, we can just say that there is a set, there is a subset, this subset is given by vector, and these are the components of the vector. It's quite easy. Okay, so there are many ways to make a classification. One of the easiest way is called the nearest mean classifier. How it works? Let us consider the classes CA given by N pattern and CB with AI and BI belonging to the training set, as I said. And an arbitrary pattern CI that belongs to, I don't know to what, maybe to this or maybe to this, okay? And we want to classify this pattern. This pattern is a kind of unknown object. I don't know if it is a dog or if it is a cat. And what I want to know is whether it's more probable that this object belongs to the set of the cat and the set of the dogs. So, what we can do is a very, very simple thing in a classical, in a standard pattern recognition model. So, we can consider, well, it is just an algebraic representation, theoretical representation. If we want to make a kind of geometrical representation, well, if we just confine ourselves to consider two features vector, okay, two features pattern, we can consider, for instance, a very easy way. Well, this is the first class of object, there are the cat. This is the second class of object, the third dogs, okay? And we can calculate just by using the Euclidean distance, the centroid of the first class, that is something like that. The centroid of the second class, the class of the dots, that is given by, for instance, this. We make the line, it is the classification line, such that all the pattern will be placed in this part of the plane will be classified as dots, for instance, and all the pattern will be placed in this part of the space will be classified as cat. Of course, by using this classification method, we have some mistake, we have some error. For instance, this dot will be incorrectly classified as a dog, even if it is a cat. Okay? So this is a standard way to classify by using the nearest mean classifier. Of course, there are many other more sophisticated way to make classification. But at this stage, what we want to obtain is a quantum representation of this method in order to have some kind of improvement. After I will show which kind of improvement we can obtain. Okay. Another thing I'd like to stress is the fact that, well, from a foundational, let me say, point of view, the notion of pattern and classification are basically very general and are naturally connected to the common processing of acquiring knowledge. So we can, using the problem of pattern recognition in many different fields, to solve many different problems. So, what we have to do actually, in order to obtain a quantum counterpart of the nearest mean classifier, we need three ingredients essentially. First of all, we need a suitable encoding from pattern to quantum object. We know that pattern we have seen are real vector. So we need to obtain a suitable encoding from real vector to quantum object. Second step, a quantum counterpart of the Euclidean distance. We have seen that the distance is essential is very important in order to have the classification, in order to establish if an object is closest to this centroid or this centroid. So the idea is distance is very important in the standard, the nearest mean classifier. So we need to obtain a quantum counterpart of this distance. The third ingredient is find a quantum counterpart of the centroid. The centroid that again plays a crucial role in the classification process. So once we have these three ingredients, we have a quantum counterpart of the nearest mean classifier. Well, first step, the encoding. is important. It's important because there are many ways to encode a real vector in terms of a quantum object. And it is very difficult to say which one is the best. Also because the pattern recognition is a kind of let me say, adaptive kind of science, in the sense that there is a theorem, a kind of, let me say, empirical theorem, the so-called no free lunch theorem, that says that it is not possible to find a classifier that is better for any data set, for any problem. It is impossible. It does not exist. But anytime we can know, maybe also in principle, which one is the classifier that best fits with the data set we have to deal with. Okay? So, similarly is in the case of quantum representation. So, I just will show you one encoding, but there are many encoding from real to quantum object that can be suitably used from one case to another. Okay? So, this is the first encoding. It's very simple. Let us consider a real vector x and y. Let me just confine in the two features vector, two component vector. So, in order to obtain from a real vector a quantum object, the strategy we do is this. We consider this real vector and we map by the stereographic map the real vector onto a surface of a radius 1 sphere. Okay? As you can imagine, each point on the surface of a radius 1 sphere can be considered on a block sphere. And that will be represent a pure quantum states. It is a very easy way to, so once we have the component of the stereographic projection, and if we put that these components are equal to the Pauli component, it is very easy to obtain from this real vector x and y this pure density matrix. That is a density operator. That is a quantum state. That is a quantum object. So it is just a representation. Okay, well, this is a very simple example. Well, what just we can stress is the fact that we start from a real space. We are coming to a space of quantum object where also complex numbers are involved. Okay, and we will call rho A the density pattern. That means that rho A arises from the vector A, from the real vector A. Okay. So, for instance, if we consider a data set, a very, very often used data set in classical pattern recognition, given by this, and if we map each point by considering this quantum representation, we obtain this representation in the block sphere. The classifier in the classical, in the standard pattern recognition is a line. The classifier in quantum, in our version of quantum pattern recognition, is a plane. So each density operator, every density operator that is in one part of the plane is considered as blue. Each density operator is in the other side of the moon is considered as green. Okay? It's just a translation. So there are many, as I already said, there are many other ways to translate a real vector onto a quantum. Yeah.
Do you take the probabilistic metric on the surface, or you go to the...
No, till now I am not considering anything. Yeah, well, in order to make this, I will consider the trace distance, just the trace distance. I will see this. So I will not consider a Fubini study. I will not consider distance between state in terms of Fubini study, but in terms of trace distance. But I have to say you exactly which one is the trace distance, because it is not the standard. It's just the point is just arrived. Thank you for the question. Is important. So, well, it is just what I said. Well, what is the distance we have used in order to put this plane? That is the question that our colleague asked. It's the right question, and it is based on it is modeled ad hoc in the sense that what we want is a distance that preserves the order. It is absolutely important because we want that if A, B, and C are real vector such that their correspondent density of, such that A is, such that they have some kind of order, okay, some kind of order, such that A is less or equal than B, less or equal than C, in the case of Euclidean distance, considering the real space, I want that when I introduce a quantum distance, this order has to be preserved among the quantum objects that arise from A, B, and C. So this is just what I said. That let A, B, and C three arbitrary patterns, and let rho I be the density pattern associated to I. If the distance between A and B is less or equal to the distance between B and C, I want to find a quantum distance such that this quantum distance between rho A and rho B is less or equal to the quantum distance between rho B and rho C, where rho A, rho B, rho C are the density pattern arising from A, B, and C, and that has to hold for any real vector and for any density pattern, okay? So, just in order to get it, we use a kind of, we say, normalized trace distance, in the sense that, well, we use the trace distance with this factor, this factor that is dependent on the vector, and so we prove that if we multiply the standard trace distance with this factor, we obtain exactly the Euclidean distance. Okay? So this is a distance between density pattern that mathematically corresponds to the Euclidean distance between real vector. Okay? This when we can exactly replace the standard nearest mean classifier by translating in terms of quantum object. Okay? Okay. If there are any questions, please stop me in any moment. Okay. In this way, we can replace the same strategy in order to make a classification. So we say that given A and B, and given the centroid CA and CB calculated by using this normalized trace distance, okay, we say that if the trace distance between rho A and rho X is greater than the trace distance between rho B and rho X, we say that it's more probable that X belongs to A. We can make some assumption related to X, not to rho X. This is the important point. So that by exploiting the quantum formalism, we can obtain some information about the initial real object. Okay? So, till now, we have considered at this stage the definition of centroid unchanged. Yep.
The centroid would be then in the interior of the cone.
Well, no, the centroid at this stage is just the translation of the real centroid. Okay. I not calculate the centroid again. This is just another crucial point. At this stage, what I have is just, I make the translation from real to quantum to each data of the data set and also to the centroid. So I'm not calculating the centroid. I'm just, translating the centroid into a quantum object. So, in this way, I have exactly a translation of the nearest mean classifier in terms of quantum object. So, the question is, which one is the convenience? Till now, the convenience is only potential, in the sense that once we can use a quantum computer properly, we are sure that we can perform a nearest mean classifier in a very, very booster way. We can just boost the process, and we can have the good convenience, not in the decreasing of the error, because the error will be exactly the same, because the classification will be the same. but we have some convenience in the efficiency of the problem, efficiency in terms of time, okay? So till now, we are not reduced in any way the correctness, okay? The efficiency in terms of decreasing the error of the process. But the point is just the centroid, So, if we decide to use another centroid that is defined in this way, the centroid is, now we consider again the data set of real point, we consider the respective set of density pattern, and we calculate the centroid in this very, very intuitive way. So, it is easy to realize that this density, well, if I consider the density pattern associated to this centroid, this row is totally different to this. Of course, for a very, 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 very simple way, a very simple reason. This is a pure state. This is not. Generally, it is not a pure state. In this way, what we are considering is something that is purely quantum, okay? Purely quantum in a mathematical sense, okay? As Sandro said yesterday in his nice talk, also in this case here we are considering the quantum formalism without carrying on its physical motivation, its physical meaning, but we are just using the formalism, okay? Because just because it is useful, because it carries some convenience in our classification, as I will show. So, I consider this centroid that has not any classical counterpart, that has not any kind of classical meaning in the standard classification process. So, why I use this? I use this because it seems to be, in a certain sense, sensible with respect to distribution of the pattern. In the sense that, well, if we have, let me again consider this very simple distribution of pattern, but also this. Okay, oh well, there is the picture here. Well, if we consider these two, the blue distribution and the green distribution, we can see that if we calculate the classical centroid, in both cases is given by the red point, of course. But if we translate the blue point into density pattern, after we translate the green point in the density pattern, and we calculate the quantum centroid by using this, we can obtain that these two sets are different quantum centroid. So differently from the classical case, it seems that the quantum centroid has some, let me say, knowledge about the distribution of the pattern, okay? Or at least it is sensitive on the distribution of the pattern. Okay, and it is given, for instance, well, I consider this kind of handwriting picture, okay? The 0 and 8 are kind of number that has the same centroid, that is just in the middle point of the box, okay? In the central point of the box. But of course, the distribution of the shape is completely different. Okay, so now what we do is just a comparison between the nearest mean classifier and the quantum classification process based on density pattern and quantum centroid by involving different kind of data set. So we are just now comparing the standard method and our classical method in terms of error. In terms of error, in the sense that we calculate the ratio between the correct classified pattern and the pattern and the total and the cardinality of the data set. Okay, and so well, let me show this. This is a data set. This is the full data set. Okay. Just at the beginning, after I will describe the entire procedure, but just at the beginning, we can consider this as the total data set. Is an artificial data set. Of course, it's quite mixture, where the red and the blue point, of course, are very mixed with one another, because, well, of course, if we consider data set like that, well, there is no difference between the quantum and the classical, because everyone is perfect, is very easy to classify. But we consider a case where the classification is not trivial, of course. So, we said that by considering the nearest mean classifier, we have that, well, we put in the picture only the correctly classified pattern by using the classification process, okay? So, we can say that by using the NMC, we have this picture. By using the quantum classifier, we can see that we have more and more patterns that are correctly classified. Numerically, let me focus on the error only, okay? Numerically, we have that the nearest mean classified success as an error equal to 0.44. So that means that error equal to 44%. The quantum one is a big, is impressive decreasing of the error because it's 24. Okay? Well, the standard way to make the classification is given by, well, given a data set, given a data set of many points, what I have some part of the data set that I use as a training set. This is just used in order to calculate the synchrony in the classical case, also in the quantum. And I perform all my calculation in the rest of the data set. I replace the same thing some hundred of times, and at the end I have some statistics. This is just the standard way in classical, and it is just what we replace it on also in the quantum framework. This is just why you have the error with this plus or minus, because it is a kind of statistical data. Well, a remark. Even if the error in quantum classifier is lower than the error in the nearest mean classifier, anyway, that could be some pattern that is correctly classified by the classical the classical procedure, and it is incorrectly classified by the quantum one. Okay? So, it makes sense to make a merging between the two methods, the classical and the quantum. And by making this merging, we have a further improvement in the decreasing of the error, as depicted in this picture. So, we replace the same, well, and for instance, we start from the 44% of error. In the quantum case, we arrive to the 24% of error, and matching both together, we obtain the 13% error. I think it's quite.
This is now the version together.
Well, just with Mathematica, well, we can just label each pattern, and we can say, well, we have the plot of the correctly classified. Well, just by matching this with this, is just the union between these two pictures. It's just the union. Of course, some data will be correctly classified for both classifiers, but sometimes, well, this set is highest with respect to this. But anyway, there is some point here that is not classified in this classification process. So if we make a sum, just a sum.
So you put the same weight, that's what it means. Because could you also imagine to have the weight as an additional degree of freedom, saying I believe 60% the quantum
exactly.
and the other one.
Exactly.
You don't try this. You just stand equal weight.
Yeah. Yes, exactly. Okay. So we do the same for plenty data set that are that are only artificial data set that are very often used in classification problem just in order to analyze which is the error. Okay. So for instance, this is the case of Moon data set. In the case of Moon data set, we have this is the NMC, this is the quantum classifier. In this sense, the quantum and the quantum plus NMC are the same because in this case the quantum classifier is always better to the NMC. So in this case, that does not make sense to make a merging, okay? And the data are given by this. So we have 0.22 of error in the NMC case, and 0.18 error in case of QC. Well, just another case. Well, this is a very particular case because it is totally totally mixed. In a certain sense, you can see that by using the classical classifier, you can never recover this part of points because are blue and all on the other side, okay? Or this part of points because are red and all on the other side. But it is possible to recover something by using the quantum classifier. And by merging both, we have a picture that is reasonably better with respect to this. And numerically, again, we have something like that. So this is the decreasing of the error from the 44% to the 34%. It's 10% of error we are recovering. Okay, and so, well, we are considering also some data with 3 classes, because till now I have only considered 2 classes. Well, it's just a matter of convention, but we can consider the case of many classes without loss of generality, okay? And this is a case with 3 classes.
That corresponds to a hyperplane arrangement, or?
No, I'm not speaking about the number of features, but the number of classes. The number of classes means that I have 3 possibilities of classification.
No, but the 2 classes you get by 1 hyperplane.
Yeah. Oh, yes. Of course. Yes. Yeah. There are 3 hyperplanes. There are 2 hyperplanes. There are 3 hyperplanes. That because they are from the 1 to the 2, from the 2 to the 3, and from the 1 to the 3. So there are 3 hyperplanes basically. But basically, we don't calculate the hyperplane because just by the programming we just say, give me which one is in the class. So the hyperplane is just in order to depict something. So in order to have a visual correspondence between this and this. But we never calculate the hyperplane. Okay, and this is just a table with a number of examples where we consider data sets that are sometimes given by different number of classes, but also different number of features. What we can see here is the number of features are involved in the data set. And we can say that quite almost, the accuracy in the classical case is less than the accuracy in the quantum case. So this is just the main result we have. So, well, it is important to stress one fact. Of course, we are comparing only the quantum case with the nearest mean centroid. And of course, there are, as I said at the beginning, more sophisticated way to make classification. So it is not, I'm not saying that this method is the best way in the world to classify, but I'm just saying that if we confine ourselves in the nearest mean centroid classification, and if we put this strategy to make a purely quantum version of this, we have almost always a remarkable convenience. Okay. Well, but we realize the strange thing. We realize that if we consider a data set, and if we translate, we have a moving of this data set, just a translation of this data set, we have that the error change, the classification process, is sensible by a translation. It is quite strange. It is not any kind of, how can I say, real counterpart. Because of course, let me consider this problem with some kind of classification. If we put this problem, and if we draw this problem, instead of this keyboard, in that keyboard, we have another rate of error, another error in the quantum case. It is very strange. It is arise from the fact that our quantum centroid is nothing related to the real. So it is, in a certain sense, we can attend that something not real can happen, okay? So, but is this a problem? Basically, yes, but we can consider, well, if we in principle know the kind of distribution we are to dealing with, we can study it at the beginning, and we can say that we can just select ad hoc the translation we want to do in order to have a further improvement in the reduction of the error. What I show in this plot are just this case. In the case of banana dataset, the one I showed you before, this line means the error without rescaling. But we know that if we make some rescaling of all the data set, some rescaling or equal to 1 point something, we have a remarkable further decreasing of the error. So that means that if we have to deal with a data set that we know in principle that the distribution is something like a banana distribution, it will be convenient in principle to make a translation, after to make the transformation in quantum terms, and after to make the classification. In this term we have two ways to gain something. The first is given by the quantum algorithm, let me say quantum strategy. And the second is given by the translation, okay? So, as a further development well, it is just, basically it is just, I think, a beginning of a study. Because till now, what we have showed in the talk is based only on artificial data set, not real data set. What we really like to do is to apply this, first of all, compared with also other kind of classifiers, as I said in a bit. Second thing, applied to real data set. In order, for instance, to solve some kind of handwriting problem, fingerprinting recognition, face recognition, and most of all, it is just what will be my desire in order to explain to someone why you make research if you are a theoretical. Well, if in my future I will be able to solve some problem related to pattern recognition applied to biomedical imaging, I will be very happy. And I just stopping. What will be the next step? First of all, as I said at the beginning, the choice of the best encoding is a different topic, because I don't know in principle which one is the best encoding, which one is the encoding able to guarantee me the maximum decreasing of the error, okay? And this is just what I like to study on, because as I said, we have several ways to encode, and it will be will be nice to detect a kind of problem that will be better solved with this encoding, another kind of problem that will be better with another encoding, okay? And another thing we need to do, till now we make just how can I say, a representation in quantum terms of the nearest mean classifier. But as I said several times in the talk, there are more sophisticated way to use classical standard model to make classification. And we can do two things: compare this model with this more sophisticated model, or maybe prepare, or maybe just assemble the same kind of parallelism, but starting no more from the nearest mean classifier, but from the more sophisticated way. So it is obtain the quantum version of all other kind of classification process. Okay, that's it, and this is the references of the work I am just introducing. Okay, thank you.
Now we're going to a round of questions.
So you consider only the blocks field corresponds to the state space of one field. So if you have higher dimensional data than two-dimensional, did you also try to consider higher dimensional state spaces?
Yes, this is a good question. We have some problem in this, because, as you know, if I consider to make, what happened? Okay, if I make this representation in a hyperblock sphere, there is some problem because there is some point on the sphere that is not a density operator. Because if we make for instance, the three-dimensional block sphere, that cannot be represented here, there is some point in the surface of the block sphere that is, I don't remember which kind of property lose, but there is not a density operator. So,
the approach would be somewhat different. You consider the space of all density matrices.
yeah,
And those matrices that have rank 1.
yes.
In the pure states, and it's not always a sphere.
Yes, this is just what we did, and this is just from a geometrical point of view. This corresponds to consider just some portion of the surface of the 3 or 4 or n dimensional hypersphere. It allows us to make the same for any dimensional vectors. Anyway, from a computational point of view, it turns out to be very, very easy. Very, very easy because when you increase the dimension, the number of components increase exponentially. Not linearly, but in a very, very big way. So if you already go to the three-dimensional sphere, you have density operator with 7 different variables. So it's quite hard. For this way, we consider also other kind of translation. For instance, this one. This one is another translation that is very easy because you have not this drastic increasing of the component we have to consider. Because if you increase the dimension of one, you will increase also the quantum representation of one component only. So this is the problem we are investigating on actually, the encoding. Because the problem is not to find the encoding, because there are so many. The point is that to find the better in which sense? The better in order to gain the best reducing of the error, but also that has to be easy to write and easy to compute.
Thank you very much for the talk. I enjoyed it a lot. I just have some questions. It looked like when you make a mapping between the distance and the distance in the quantum line, so you're basically shifting the distance. So you have the Q, the K constant vector is basically
Yeah.
the data. So the other thing is when you were classifying the data set, it seems that the quantum classifiers seem to have to make a non-linear classification. Yeah, the classical one made a linear one.
Yes,
And
exactly.
the quantum one was able to put non-linear. Since you basically are comparing like a linear kernel with a non-linear kernel,
Well,
arise from the quantum one.
Well, basically, the way to classify, I think, is linear in both cases, because the classification function comes from to be a line to a plane that is linear again. What is non-linear is the distribution of the points, because I'm forcing it in a sphere. So, in this sense, yes, I agree with you, and I think that is the reason why this problem in the translation happens. I think. But anyway, very often, in any case, we have some topological problem. In quantum case, this kind of problem very naturally arise, and generally are not, well, like I say, are not problem, in the sense that, well, if my approach, well, the point is that my approach is totally, how can I say, classical. I'm using the quantum just because I see that it works, basically. And so, I am not very, very careful about the fact that the geometrically perspective is embarrassing in this sense, because I expect this. I'm waiting for this. But when I make the error, I said that, well, this is an increasing, and I see this is just what I noticed.